Hi and welcome to the Optical tutorials. In this video we will cover how to run an analysis with Optical. Previously we showed how to set up project properties using the region of interest buttons. So let's assume you've got that done already. And so we're still looking at this UCLA project. You can find more information about it on the website. Okay, so as you can see, I have about 1,000 images here and I only provided a few for the tutorial, but the real project is several thousands of images. Okay, so this module may appear a little obscure to some of you who are not familiar with the digital image correlation. So I'm just going to explain in simple terms how you're going to set up your parameters here. So first, let's look at this box here, the subset parameters. You have two sliders, the subset size and the subset spacing. So you may wonder, what is a subset? So let's look at this PowerPoint here. So this is our wall, and this is a zoom on our wall, and this is a subset here. A subset is a very small region, in this case 35 pixels by 35 pixels, that the software will use to match. So it will try to match this region as well as possible when it's going to look at the other images during the test. So the larger the size, the more pixels the software will have to find a better fit. However, the larger the box, the less details you're going to get in your projects, right? So you want to have a subset size such that your software has enough contrasts and enough features to work with. In this case, you can see that in this little box here, I have a few spots. So I have a lot of contrast, I have a lot of blacks, I have a lot of white. So the software will handle that subset really well. So I would probably keep it this way. This is a subset 3 times bigger here. So in this case, you can see I have a lot more features to look at. And so the result will be that the software will average over a larger region when computing the results. You may want to grow your subset size when you have poor quality pictures, for instance. So you had a camera with 25 megapixels and so on. However, you did not manage to get enough sharpness and so on out of your picture. So you end up with really poor results and you want to do some analysis out of it. You will need to grow your subset size in order for the software to simply get a result. So that's it for the subset size. Now the second parameter is the subset spacing. Subset spacing is the distance between two subsets. And the subsets do overlap, so it's a very important parameter you need to understand. So this is a 35 pixels subset with a 13 pixel spacing here. So you can see that the next subset will actually overlap over the previous one. So the subset spacing will define the resolution of your color map later on. The smaller the spacing, the more subsets you're going to have. And so the more resolution your color map will have. So you may wonder, why not use 2 pixels subset spacing and have the best definition you can get? Well, at some point, it stops making sense to reduce the subset spacing because you're pretty much measuring over and over again the same region. For instance, here, let's say I have a 105 pixel subset size and I picked an 8 pixel spacing. You can see that the next subset is almost the same than the previous one. So in other words, my solution will have a really, really good resolution. It'll have a lot of pixels. However, the result will be as if it was filtered. Each subset covers a large region of my image. So the color map will look a lot more filtered. It will have a lot less detail. For instance, if I have a crack or a discontinuity, this discontinuity would be smeared on a larger region. So it is usually preferred to keep reasonable numbers here, right? An overlap of 2/3 of the previous subset, for instance. In other words, if you have a subset size of 45 pixels, a good subset spacing is somewhere around 1/3 of that. So 13 pixels is pretty good here. So that's it for the subset parameters. I hope it makes sense. The next parameter is the seed. So that's another feature about image correlation. The algorithm will use the solution of the previous subset to compute the next one. And that's how it's going to spread. So it needs to start somewhere. That's why in Optecal you need to define what we call a seed. If you hit that button here, you can draw a seed anywhere you want. Let me explain what we're doing here. So the algorithm will search very accurately for that particular seed with a computer-intensive algorithm. And once it has a rough location of that seed, it will start to propagate from there. So as a seed, you want to pick a point that is really well defined. In other words, if I have a big crack spreading on my specimen, I would not pick that point as a seed. So in this case, for instance, let's pick this region. If I'm afraid that this specimen will be heavily split in half, and so I'm afraid that this seed will not be able to propagate past that crack, it would have to be a really, really serious crack to be the case, but let's assume so. You can always draw a second seed. And so now the algorithm will spread from two different regions. So that's very handy if you have a specimen that turns that completely splits in half and ends up into two separate bodies. Having two seeds like this allow you to keep track of both. Okay, and you can see that there's a big box around each seed here. It is the initial region search box. So in other words, the software will look for that seed in this particular region. So you must make sure that your seed will remain in this box throughout the entire experiment. And you can define this size here. So right now the box is 500 pixel wide. And I can define it as 2000 pixel wide, for instance. And don't be afraid to be generous here. There's really nothing wrong with picking larger boxes. It's very, very rare for the software to have to pick an alias. In other words, to pick a point somewhere else on the image that is very, very similar, but not the point you're looking for. It is a very, very rare event, so don't be afraid of picking a large region. If your analysis for some reason does not work well, maybe this is your problem. You can start to reduce this region, but again, very rare event. Don't worry too much about it. Also, don't worry if your box is outside of the region of interest. The software will never alias any of this part of the region as your subset. Okay, they're way too different. So having features that are outside the region of interest is of no importance at all. Don't worry about that. Okay, then you have a few more parameters. The spline interpolation here is something very technical about image correlation. I won't enter into details here. If you know a lot about image correlation, you might be interested in tweaking this parameter. The correlation coefficient rejection is how far from the initial subset you allow your software to be. In other words, when your software, when Optecal tries to match the initial subset and a heavily deformed subset using its shape functions, if the result is not within 90% of the initial subset, it will reject this solution and consider it a fail. 10% is a good number here. I wouldn't tweak this number except if, for instance, I had a poorly lit image and the correlation turns out to always be very bad and very noisy, but I still want to get some result out of it. I may want to bump this number. That's about it. Otherwise, I'd leave it there. Okay, then you have two more buttons here. You have the perform high strain analysis. So that is for the cases where your body deforms a lot. And there is an example on the Optecal website about that. So a lot means in the order of 100% strain, 200% strain. So in this case, the software cannot use the reference image to compare each deformed image. It must update the reference because it's changing too much. So in that case, the chronology is important. All right, it's important that in order to solve the third image, you've solved the second one. And in order to solve the fourth image, you need to solve the third one. The software needs that history to progress for very, very high strain analysis like this. So you'd pick that button only when you're testing, say, steel coupons with a lot of ductility and so a lot of plasticity, or rubber specimens and so on. For this wall here, I can show you the very last image. This is not considered like a lot of displacement here, so I would not use the high strain analysis tool for this experiment at all. Okay. Last but not least, this button here, use all CPU resources. So this is up to you. It's just that Optecal is a multi-processor software, so it'll make use of your computer, of all your computer resources. However, if it starts using absolutely every single core of every single processor you have on your computer, your graphic interface will get very, very slow. So if you want to be able to keep surfing on the web or work on a Word file while you're running an analysis, you should uncheck this box. And what it's going to do is simply Optecal will free one processor so that your graphics interface can still run properly. So for instance, if you have a 12 cores computer, if you uncheck this box, it means that Optecal will only use 11 and leave one core so that you can run basic tasks on the computer. If you decide to let your analysis run all night and you don't intend to use your computer at all, might as well click that button here, let the computer have 100% of your computer resources, and the graphic interface will be unresponsive, but who cares if you're not using it, right? Okay, so once you've defined all these parameters, you can select your images. So you can use Shift and Control, like this, for instance, and analyze the selected images, or simply hit the Analyze All Images button. Now be aware that we're working with really, really large files here. So you gotta give your computer some time to compute this solution. For instance, here we have about 1,000 images. So on a laptop with Intel i7 processors and so on, so just a high-end consumer-grade laptop, you would expect this analysis to take about 8 hours to be performed. If for some reason the computer crashes during the analysis, no big deal, you will have all the results saved up to the point where it crashed. And so you will see when you look at your results, if there is no result, and we'll go over that module in another video, if you cannot see any color map, it means the analysis crashed at that point, right? And so you would simply start the analysis from that point, select all the other images here, and run the analysis on that, right? And that would work just fine. Even if you were doing high strain analysis, it would recover the previous solution and work just fine. So don't worry if your computer crashes while processing the very last image. You have not lost much. Okay. Every time Optecal solves for one image, it stores it onto your disk, and so you can always recover it. Okay, so that's it for the run analysis module. That's clearly the one that requires a bit of theory about digital image correlation. So what you need to understand is simply what's a subset. So it's a small box, about 30 pixels wide. And what is the spacing between these subsets? So remember that the subsets can overlap. So I'll show this image again. Subsets may overlap. And so that's pretty much what you need to understand, that the definition of your image will depend on the spacing, and the level of details will depend on the size of this region. I would start with the initial parameters, the default parameters, which are 45 and 13, and see what you get. Also, don't hesitate to run analysis on a single image. Pick an image that's well advanced in your test and see what you get. Just run a single image, play with the parameters, see what you get, see which one you like most. And once you picked your parameters, just apply them, just select them here and run the analysis for the rest of the experiment. Okay, thank you very much for watching. Next video will be on how to format the results display. Thank you very much.